Hi there. I am going to tell you about our recent ALMA observations of a stellar merger remnant of V3 Monocerotis, where a merger ejecta composed of molecular gas and dust interacts with a distant hot companion. That interaction produces shocks that are very apparent in molecular emission. Although very recently a few other shocked circumstellar environments have been observed around eruptive stars, there is practically no framework to understand their molecular abundances. V3 Monocerotis, most famous for its spectacular light echo, erupted in 2002, reaching a luminosity of 10 million solar luminosities, becoming for a few weeks the brightest star in the local group of galaxies. The eruption was caused by a merger in a triple system with two B-type main sequence stars and a low mass protostar. For unclear reasons, one of the B-type stars merged with the low mass pre-main sequence stars. For this presentation, however, it is important to note only that the merger event was associated with a heavy mass loss. The m dot values corresponding to the event were of the order of 10 power minus 3 solar masses per year, and the ejecta velocities were of about 500 kilometers per second. The fast ejecta was composed in big part of molecular gas and dust, and while it was expanding, it finally reached the B-type star. The radiation of the B-type star started photoionizing the merger ejecta, and we witnessed that moment as well. We saw flaring of emission lines, in particular of FE2 lines, that allowed us to actually measure the distance between the two stars. A few months later, the B-type companion completely disappeared from optical observations because it became enshrouded in the dusty cocoon of merger ejecta. Now, moving fast forward to 2019, we were able to map the merger remnant with ALMA at its longest baselines and with very high resolution. This allowed us to map the system in a few molecular lines and in continuum. The molecular lines are here represented by colors. Contours represent continuum emission. And the main peak of the continuum emission corresponds to the position of V3 Monocerotis. The secondary peak shows us the cocoon of the B-type star. We see a third component, which is an extended cloud. That cloud was most likely created through the interaction of the radiation pressure of the radiation of the B-type star with the dust grains in the merger ejecta. Molecular lines also show us the signs of interaction between the B-type star and the merger ejecta. That is caused mainly by the gravitational attraction of the B-type star. So we're dealing with gravitational focusing, so the trajectories of the particles start to intersect behind, up the flow, behind the B-type star. So we see we expect collisions just behind the B-type star. And also it's being accelerated. And that's why we see the molecular remnant being more extended along the line connecting the two stars. There is also weak but very fast wind of the B-type star that interacts with the merger ejecta, making the entire configuration rather complex. But we do see the evidence of shocks in the distribution of molecular gas. Here I am showing you the emission of aluminum hydroxide and sulfur hydride that peak exactly in the position where we expect the shocks to occur. Here I'm showing the emission in a single line, but we can think of those maps as the abundance distribution, and we think that actually those molecules are being formed most effectively in those shocked regions. A counterexample is gaseous SiO, which is completely depleted in the interaction region. Here I am showing you channel maps of SiO distribution at different velocities. And based on those, we are able to reproduce the three-dimensional surface of the SiO cloud, where you can see clearly there is a void exactly at the position of the interaction region. Unfortunately, there is no theoretical framework that would allow us to understand these molecular abundance patterns. The molecular effect in shocks is very clearly seen in V3 monocerotis, mostly due to the fast speed of the ejecta and high densities. But such interactions take place in other systems, including VVSFA type stars or wider systems such as Antares AB. Furthermore, there is a lot of recent discoveries of exotic molecules in eruptive variables that challenge our understanding of the molecular envelopes. And the most remarkable example may be the observation of methanol in Eta Carinae or in CK vulpecula, where we did not expect to see those molecules. These discoveries call for more theoretical work on shock chemistry, and I would like to encourage any theoretical work on formation of molecules in circumstellar shocks. In the meantime, I'm considering obtaining a survey of such media to get at least a phenomenological view on those environments. Finally, I welcome any comments or questions concerning V3 monocerotis or the shock chemistry. Please contact me on Slack or via the email, which is given in the corner here.